Some of the most important information in astronomy comes from the technique of spectroscopy, which involves dispersing light into its constituent wavelengths, as Newton did with his prism hundreds of years ago. Looking at an image of this star cluster, all we see is the stars. Maybe we can measure their colors, but there's little extra information here. Look instead at this star cluster where we can see the spectra of every star within it. From these spectra, in work first attempted 100 years ago, we can learn not only the temperature of the stars, but also their density, their composition, and parts of their life stories. Spectroscopy gives us a lot more information than just taking an image. It is one of the most powerful tools of astronomy. It gives us remote sensing for physical conditions far away, millions or even billions of light years away. To talk about spectroscopy, we have to look at the way that light interacts with matter. Essentially, everything we know in astronomy comes from the interactions of light or other forms of electromagnetic radiation with matter. We are using remote sensing to learn about distant objects based on the radiation they emit or absorb. In principle, light can be emitted, absorbed, scattered, or reflected from material and material objects like stars. We use terminology like transparent or opaque. A gas or an object that is invisible to radiation or where radiation cannot be transmitted is considered opaque. An object where radiation is freely transmitted without interaction is considered transparent. We're familiar with some of these interactions in our everyday life. It's important to be clear about the distinction between the apparent and intrinsic properties of something. When you look at something like a wall or a sweater that appears to be red, that's not because that's thermal radiation from the object, reflecting its temperature. That's because of a pigment or dye in the paint or the dye used for the cloth, and it's what that radiation from the sun or from an overhead light reflects and absorbs. An object that appears red, in that sense, is just reflecting the red part of the visible or white light to you while absorbing the blue light. That's quite different from the thermal radiation, where a blue object is a hotter object and a red object is a cooler object. To dig deeper into the interaction between light and matter, we have to look at how light interacts with individual atoms. It was learned about 100 years ago that the atom does not have a continuous set of energy states. It has a quantized set of energy states. This is the basis of the so-called quantum theory of atomic structure. It was first understood by Bohr, Heisenberg, and others in the early 20th century. In other words, atoms cannot have any energy, and they cannot exchange energy in any amount. They can only absorb or emit particular amounts of energy corresponding to their particular energy levels, the quantized energy levels of an atom. Every single unique element with a unique number of protons and electrons has a unique set of energy levels that mark it out. It's like the fingerprint of an atom. And it, of course, means they have a spectral fingerprint as well, or a set of photons that can be emitted or absorbed that's completely unique to each chemical element. Taking the simplest element, hydrogen, it has a set of energy transitions corresponding to energy that it can lose or gain. And these energies map, by the electromagnetic spectrum, into particular wavelengths or frequencies of light. So hydrogen, if it's excited or if it absorbs energy, has a particular fingerprint of possible transitions, its spectrum. This was first seen over 100 years ago. We can take a Bunsen burner and heat up chemical elements and then disperse the light that comes off or is emitted by those elements with a prism, and we will see these particular emission lines or sharp spectral features at particular wavelengths, and they are always unique to the element. In these examples, we see the uniqueness of this imprint. Hydrogen, helium, and heavier elements like neon and mercury have particular sets of transitions. The appearance of the spectra from these objects to the naked eye is based on the combination of all these ingredients, because the eye does not disperse into a spectrum. But in the case of neon, we see that a lot of the energy comes in two particularly intense lines in the red or orange part of the spectrum, which gives neon signs their purity of their red characteristic. Other elements like helium have spectral lines across the blue, red, and yellow parts of the spectrum and so emit a duller glow of yellow or pale yellow light. Regardless of the particular characteristics, the fact that each element has a unique spectral signature means that if you have a combination of these gases, those elements just add. If you have a mixture of hydrogen and helium contained within a gassy experiment, you'll see the lines corresponding to the sum of both the helium lines and the hydrogen lines superimposed on each other. Working this logic backwards, that means if we had an unknown gas and dispersed its light into a spectrum, we could diagnose the chemical ingredients. Spectroscopy actually allows us to go further. If we have good enough spectroscopy, we can actually look at the profile or shape of those sharp spectral features and infer the temperature or the density of that hot gas. And that's how we learn about distant stars. The spectral fingerprint is an extraordinary sensitive technique. In astrophysicists' hands, we can detect the presence of trace elements in a star at constitutions of 1 part in a trillion relative to hydrogen or helium. Extraordinary trace elements. All this information can be combined to say what the universe is made of in terms of constituents in the periodic table and their abundance relative to hydrogen and helium, the most abundant elements. In astronomy, we tend to see 3 different types of spectra. One is the spectrum emitted by a hot gas, such as a discharge tube. This is where the gas is excited and emits the narrow, sharp spectral features corresponding to its element. This is called an emission spectrum. We can also see the smooth spectrum that just results from the random motions of atoms or molecules in a gas. And this is the smooth thermal spectrum, which would peak at optical wavelengths for a hot object like the sun and at infrared wavelengths for a cool object like a planet. The third type of spectrum we can see is when a hot source has a cooler envelope of gas outside it. In this case, the high excited transitions are absorbed by the cooler gas, but again with the characteristic fingerprint of the element that gas is made of. This is actually what the sun spectrum looks like, because the hot fusion core is surrounded by cooler outer layers. These 3 types of spectra, to astronomers, are called a continuous spectrum, the smooth thermal spectrum of a hot object, an emission spectrum from a hot excited rarefied gas, and an absorption spectrum where the hot excited gas is surrounded by cooler material. The rules by which these 3 spectra are produced are called Kirchhoff's laws. Another very important attribute of radiation in astronomy that's diagnosed by spectroscopy is the Doppler effect. The Doppler effect is familiar to us from sound waves, but it applies to any form of wave. In the Doppler effect, a source of sound waves has those waves compressed in the direction of its motion. When the ambulance approaches you, it's catching up with the waves that it emits, compressing their frequency and raising the pitch. And so you hear the rising pitch of the ambulance. When it's receding from you, it's moving away from its waves, stretching out their wavelength or pitch, or lowering it, and you hear the lowering tone. That's a very characteristic phenomenon for sound waves, but the same thing happens with light waves, or any electromagnetic wave as well. And so in terms of light waves, the Doppler effect corresponds to the fact that if a source of radiation is moving away from us, the wavelength is shifted towards the red compared to that source being stationary. And if that source is moving towards us, the waves are squashed or compressed or shortened compared to that source being at rest. So we have red shift for objects moving away from us and blue shift for them moving towards us. The percentage of the shift equals the velocity of the motion relative to the speed of light. Since the speed of light is a very large number, 300,000 kilometers per second, and the motions of most astronomical objects are much smaller, maybe tens or hundreds of kilometers per second, a Doppler shift is usually a rather small amount, small fractions of a percent. Even though it's a small effect, spectroscopy is such a powerful technique that it's easy to detect tiny fractional shifts corresponding to this effect. So we can easily map the motions of stars or even entire galaxies using the Doppler effect. Notice that the Doppler effect cannot tell us about the transverse motion of an object when it's just tracking on the sky in parallel to us. It only talks about the component of its motion towards or away from us. Therefore, to reconstruct the full 3-dimensional space motion of an object, we don't have sufficient information. all we are getting is one component or vector of the information, towards or away from us. Almost everything we know about the universe comes from the interactions between radiation, or light, and matter. Light can be emitted, absorbed, scattered, or reflected. Spectroscopy is the powerful technique that astronomers use to diagnose the distant universe, based on dispersing light into a spectrum and looking at the details of what's going on in the emission from an object. Hot astronomical objects show characteristic spectral fingerprints which tell us their chemical constituents, what ingredients they're made of. This technique is extraordinarily powerful and sensitive. We can detect the traces of heavy elements at a level of 1 part in a trillion relative to the hydrogen and helium that are most abundant elements in the universe. We can even use the shape of the spectral lines to talk about the temperature and the density of a distant star, or even a galaxy. Remote sensing, or the use of spectroscopy to diagnose the physical conditions of the universe, is perhaps the most powerful technique in astronomy. We can also measure the Doppler shift, or the relative space motion of an object based on its waves being compressed or rarefied due to its relative motion with respect to us.